Welcome to the first lecture where we will be introducing the course and providing some motivation for the content that will be covered. Even before the start of this lecture, I will emphasize that this course requires you to be familiar with the basics of convex optimization. In case you are not feeling confident, I would request you to please revise the fundamentals of formulating, manipulating and solving convex optimization problems. More importantly, you should be aware of the importance and role of convex optimization in an application of your choice. So as you may know, most convex optimization problems, that is optimization problems with convex objective and convex constraint functions, can be solved using interior point methods with complexity order n cube, where n is the number of variables or constraints, whichever is larger. For those of you who may be unfamiliar, when we say that the computational complexity grows as n cube, you can think of it as the total number of elementary operations, say addition, subtraction, multiplication, division. This number is given by some problem-dependent constant times n cube. That is, if you increase the n by 2 times, the computational complexity will increase 8 times. If you are running this on a computer, the time the computer spends on calculating the solution will also scale similarly with n. Such computational complexity bounds are very useful in studying algorithms. So note that for several decades, it was not known if general convex optimization problems could be solved in polynomial time. The question was finally resolved around 1984 when interior point algorithms were first proposed for solving linear programming problems and were shown to have complexity that was polynomial in n. These algorithms were subsequently refined and used for solving a wide class of convex optimization problems, and their computational complexity was also improved. If you consider their modern avatar, the computational complexity of interior point methods grows as n cube. This is in contrast with other more difficult problems such as integer programming problems, where algorithms have computational complexity that grow exponentially with n. So in that sense, we say that convex optimization problems can be solved efficiently using interior point methods. Notwithstanding the success of interior point methods, they still are limited to small or moderate sized problems. On the other hand, many problems in machine learning and signal processing are high dimensional. That is, for these problems, n may be so large that n cube is unthinkable and interior point methods cannot be applied. For example, consider the Netflix prize problem, which was announced around 2008. As you may know, Netflix is an online movie streaming platform. They were primarily interested in building a so-called recommender system, which would be able to generate personalized recommendations for movies to a user. Recommender systems are not unique to Netflix, but in fact they are widely used in e-commerce like Amazon. Netflix had a bunch of movie ratings with them, and these ratings were arranged in form of a large matrix whose rows represent users and columns represent movies. At that time, they had around 500,000 users and 17,000 movies. The entries of this matrix would be filled with ratings provided by the user out of 5. However, most of the matrix was empty because, as you can expect, most of the users had not seen most of the movies. If we pose this as an optimization problem, we would observe that the number of ratings was around 10 to the 8. But we would have to consider the missing entries in the matrix as optimization variables, which was around 10 to the 10. In other words, only about 1% of the matrix was filled and rest was empty. So as you can see, this value of n is so large that it is simply not possible to apply interior point methods. For such large problems, in fact, it is preferred that we have algorithms that run in time that is linear in n. That is, the number of elementary operations we want to perform should be a constant multiple of the number of variables or constraints. This is the class of algorithms this course will focus on. Note that it is not always possible to do so. In fact, we will often make several assumptions and restrict ourselves to special cases of sufficiently regular problems which can be solved in linear time. But thankfully, most of the problems arising in machine learning and signal processing will satisfy these conditions and therefore can be solved using algorithms that will be discussed here. Next, let us take a look at the class of problems that we will initially consider. The problem of interest can be written as minimize f of x, where x belongs to a convex set calligraphic x. The function f and the set calligraphic x are both convex, and on top of that we will impose other restrictions as well, so that these cannot just be any arbitrary functions or sets. Sometimes we will consider the case when f is a non-convex function. The analysis of convex optimization problems is easier than that of non-convex optimization problems. This is because for convex functions, a stationary point is also a global minimum. Suppose for a moment that the set calligraphic X is a space of all n-dimensional vectors, and also assume that f is differentiable everywhere. Then a stationary point is a point x star such that the gradient of f at x star is equal to 0. When considering general non-convex functions, you may note that a stationary point may be a local minimum or a local maximum or even a saddle point. For convex functions, however, such points are always the global minimum. This can be easily seen from the first order condition for convexity, which you already know. The first order condition for convexity says that for any y, it holds that f of y greater than equal to f of x star plus inner product of gradient f of x star times y minus x. Since x star is a stationary point, we have already seen that gradient of f of x star is equal to 0, so that the second term is 0. Hence we have the inequality f of y greater than equal to f of x star, which holds for all y. In other words, this example implies that f of x star is the global minimum, since this is where the function takes the smallest value. In particular, this property is immensely useful and allows us to guarantee that our algorithms will work and enables us to characterize their performance. Without this property, our guarantees would be much weaker. So in this course, we will not delve into the formulation of convex optimization problems. If you are into machine learning, communications, signal processing, finance, etc., it is very important for you to know which problems are important and if any of these can be formulated as convex optimization problems. If any manipulations or approximations need to be done for that. This is covered in the book by Boyd and Vanderberg, which goes into details of applying convex optimization to practical problems. I again emphasize that you should know how and when to use convex optimization before learning the intricacies of the algorithms that we use to solve them. If you do not have the bigger picture, this course might seem pointless to you and you might lose interest. Let us look at some examples where convex optimization problems of the form discussed here arise. A common framework is that of empirical risk minimization, where we are minimizing a sum of several functions fi of x plus lambda times r of x. Here r is the regularizer, fi is the loss function or risk function. This problem has a parameter lambda which is greater than or equal to 0. These loss functions arise from some data that we have stored and I is the index of those data points. Usually every data point will be in form of a tuple wi yi, where wi may correspond to features and yi to a label. So for instance, if you are looking at the problem of classifying, if a given image is that of a dog or a cat, these wi will be feature vectors extracted from each of these images, and yi would be number representing if an image corresponds to that of a dog or a cat. This is called binary classification, and in this case yi is either -1 or 1. A commonly used loss function in this context is a hinge loss function, which is given by fi of x equal to max of 0, 1 minus yi inner product of wi, x, where we have assumed that yi to be either -1 or 1. Another common one is the logistic loss function, which is given by fi of x equal to log 1 plus e raised to the power yi times inner product wi, x. If we are worried about overfitting, we might regularize these problems by adding the term rx equal to norm of x square. On the other hand, you could also be looking at the regression or curve fitting problem. In that case, wi corresponds to some features and yi correspond to response variables. For the regression problem, a common objective function is the least squares problem, where the objective function is the difference between yi and the inner product of wi, x squared. In the vanilla or classical least squares, there is no regularizer. Then there is a ridge regression, where the regularizer is equal to norm of x square. More recently, in the last 2 decades, people have used the lasso regularizer, where rx is equal to norm 1 of x, which encourages sparsity in x. Another example is the symmetric matrix completion problem, which is essentially a simplified version of the Netflix problem that we just saw. Here we have an n cross n symmetric matrix, Y, which is known to be positive semi-definite. Recall that a symmetric matrix is positive semi-definite when all its eigenvalues are non-negative. If the matrix is not symmetric, its eigenvalues might be complex, so the question of them being positive or negative does not arise. For this reason, in this course, wherever we say that the matrix is positive semi-definite, you can assume that we are talking about symmetric matrices only. So we have a PSD matrix Y that is partially known, that is, only some of the entries Yij are known to us, where I, j belongs to the set capital Omega. Omega contains the locations of all the entries of Y that are known. The values of Y at the remaining locations that are not in Omega are missing. Our goal is to find the matrix X, that is a full matrix, which is simple in some sense and completes Y. The symmetric matrix completion problem entails finding X by solving the following problem. Minimize trace of X, which is the sum of diagonal entries of X and is also the sum of eigenvalues of X, subject to X agreeing with Y on the locations where Y is given and X being PSD. There are many more problems such as these. Next, let us ponder over the question on how to characterize the performance of an algorithm. Let us look at this question from various perspectives. First, we have the perspective of an applications developer. A person developing an application to be used by customers will primarily be interested in runtime as a metric. But as algorithm designers, is runtime really that good a metric? For sure, it does provide us with the exact value of the number of seconds required by an algorithm to complete a task. However, the runtime of an algorithm is very implementation dependent. The same algorithm, if implemented properly or even on a faster machine, will have lower runtime. Further, runtime is an opaque metric since it hides away all the scalability issues that the algorithm might encounter. For instance, suppose we are interested in finding out if the Newton method is faster than the gradient descent method. The correct answer is that it depends on the problem and the value of n. This cannot be inferred by looking at runtime alone. The runtime would be better sometimes and worse in other settings, and it would be very hard to find the pattern in that behavior. Then let us take the perspective of an optimization toolbox designer who is writing code for various optimization algorithms but wants to deliver a machine-independent experience. For such settings, a commonly used metric is that of flop count, which is the count of number of floating point operations required by the algorithm. Unlike the runtime, this metric is largely machine and implementation independent. However, for us, it is still too problem specific. In fact, the flop count would be different for every objective function and constraint. What we instead want is a metric that can capture the performance of an algorithm over an entire class of problems. The metric should not vary with each actual problem, just classes of problems. This brings us to the black box model that we will consider in this course. The assumptions of the black box model are as follows. We assume that we have unlimited computational resources, so we abstract away the computational aspects. We further assume that set X is completely known. Finally, F is unknown, but the information about F can be obtained by calling an oracle or a genie. So we have access to an oracle or a genie that for a given value of X provides us either the gradient or subgradient or approximate gradient of F at X. So as you can see, we have ignored all the aspects of actually calculating the gradient and working with the set X. In other words, we have abstracted away the computational complexity aspects completely. Instead, we are only interested in finding out and ultimately minimizing the number of calls that are required to be made to that oracle. If we tweak the algorithm to reduce the oracle complexity, it will in fact benefit the entire class of problems. The key question that we are interested in answering is, how many times must we call the oracle? Suppose that the algorithm stops when the optimality gap, which is given by f of x minus f of x star, is below a certain pre-specified threshold epsilon. Then all our results will be of the form the number of oracle calls equals some function of epsilon. For instance, if we restrict ourselves to functions that are smooth and convex, then we will see that the projected gradient descent methods require order of 1 over epsilon calls to the oracle in order to ensure that the optimality gap is less than or equal to epsilon. As you decrease epsilon, the number of calls will increase in an inverse proportion. Note that this is only useful for theory. In practice, we do not know f of x star, so we cannot obviously check if the optimality gap is below epsilon or not. Instead, these algorithms either run for a fixed number of iterations or use some kind of stopping criteria that might be a heuristic. These heuristics are not covered in this course. Another point I want to make is regarding the upper and lower bounds on oracle complexity. As we have already seen, the projected gradient descent requires 1 over epsilon calls to the oracle in order to achieve epsilon optimality. There are two fundamental questions one could ask. First, if there is any other algorithm with lower oracle complexity. And second, what is the smallest possible oracle complexity achievable by any algorithm that has access to the first order oracle. These questions can sometimes be answered using information theoretic reasoning, but this analysis will not be covered here. But anyway, let us take a look at an example. Till about 1983, it was not known if gradient descent was the best first order algorithm for minimizing smooth convex objective functions. The question was resolved in 1983 by Nesterov, who provided an example which required at least 1 over square root epsilon calls to the oracle in order to achieve epsilon optimality, regardless of the algorithm being used. This implied that gradient descent is not the best algorithm. That example essentially showed that 1 over square root epsilon is the lower bound on the performance of any first order algorithm. Interestingly, he also proposed the accelerated gradient descent algorithm, which was able to achieve this oracle complexity of 1 over square root epsilon. Finally, a few points. Many of the algorithms that we will consider are dimension free, in the sense that their oracle complexity will not depend on n. If it takes them order n time to calculate the gradient, it would imply that the total computational complexity of flop count for these algorithms will be order n, if we assume everything else to be a constant. This is in contrast with interior point methods, whose computational complexity is order n cube, as we have discussed earlier. We will also consider algorithms that can work with inexact or noisy oracles. This is particularly useful in the ERM problem, where we considered the objective function to be a sum of several functions. When the size of the data is large, that is when m is large, the calculation of the exact gradient requires you to calculate the gradient for each of the FIs and then average them over the entire dataset. So if you have millions of data points, each of them would have to be read and processed at every single iteration. So you can see that the oracle has a lot of work to do in this case, and indeed the assumption that the oracle is providing us the exact gradient seems unreasonable here. Instead, let us assume that the oracle provides us only with a noisy gradient. For instance, the gradient of a single component, or Fi, is essentially an approximation to the full gradient. While this approximation may look bad, we will see algorithms that can handle this much error. Before concluding the introductory lecture, I list some classes of algorithms that are definitely important but cannot be covered here because of time constraints. These include the zeroth order and higher order algorithms, structured optimization algorithms that utilize the problem structure, such as the interior point methods, expectation maximization, the classical version of alternating directions method of multipliers, ADMM, and methods solving non-convex problems using convex approximations, such as the majorization minimization. So that is all for this video. We'll continue in the next video.